a great former star grad student, Vincent Vatter, now uprising assistant professor, soon to be associate professor, and a little bit after full professor at the University of Florida, speak about very neat stuff about permutation recordings. As usual, we're going to take Vince and the speaker, in this case Vince, to dinner at the usual place. If you'd like to join us, please let me know immediately after the talk.
Okay, thank you. So I want to talk about some automated ways to enumerate restricted permutations. So I know that's a topic that's been talked about before here. So let me just be clear. This is always going to be classical avoidance. Okay, so let's say pi, if it's in Sn, it contains sigma in Sk if, well, if there's some sequence pi by 1, pi by 2, up to pi by k, in the same relative order as sigma. So this is just classical avoidance. It's not any of the newfangled stuff. There's nothing has to be contiguous, anything like that. Okay. So for example, the way I like to think about it is just going down in the permutation is deleting letters and relabeling. So let's just take a random permutation, 3, 6, 1, 5, 2, 4. If I delete some symbols from that, maybe the 1, the 4, and the 6, then that would be 3, 5, 2, which is in the same relative order as 2, 3, 1. So that means I'm just saying that 2, 3, 1 is contained in this permutation. Okay, and the containment is witnessed by the 3 and the 5. And that's it. Okay, so I just want to be clear that this is just the classical setting. And we're going to be given a set of permutations to avoid. So this is basically our problem. We're given a finite set of permutations to avoid. And maybe I'll make a definition here. AV sub n of B is a set of permutations of length n that avoid every permutation in B. And we want to find a formula for this. So find formula for the number of permutations of length n that avoid everything.
There's always a formula.
Yes.
Sigma 1 names always the same.
Yes. So of course, there's always the caveman formula. There are slight improvements on the caveman formula. What we really want is a good formula, probably a polynomial time formula. So polynomial time n.
I hate formula.
Okay. So we're going to call it an algorithm to compute.
Yeah.
And we want it to be polynomial time algorithm, probably. Okay. And there's some doubt about whether or not we can always find this. So it's still interesting, even if all we can find is a polynomial time algorithm. It's still interesting when we can do this. Okay. So back when I started looking at this, wow, I guess it's a decade ago now, people were still doing a lot of these by hand using what were fairly unsophisticated methods. So one of these methods was generating trees. So the idea with the generating tree is that we're going to just list the permutations that avoid these patterns in a tree where the children of a permutation are all the ways we can insert a new maximum element into that permutation. So let me do an example. If I avoid say I avoid 1, 3, 2 and 2, 3, 1. Okay, well, the root is going to be the permutation 1. I can insert a new maximum element at the end or at the beginning. And then we see we can't insert a maximum in there. That's forbidden. But we can insert before the 1 and after the 2. Or over here, we can go before the 2, not between the 2 and the 1, but after the 1. Okay, so we write these out. And now if you think about it, every 2 elements are either going to be a 1, 2 or a 2, 1. So we can't insert between anything. We can only insert at the sides. So in fact, here, the children of 3, 1, 2 are 4, 3, 1, 2, 3, 1, 2, 4. Here we have 2 children, and so on and so forth. So this tree worked out to be very simple. It's just the complete binary tree. We get our formula from this observation. 1, 3, 2, 2, 3, 1. 2 to the n minus 1, because we had a complete binary tree. Now, I didn't prove that, but it's pretty easy to prove that it's actually going to be a complete binary tree. Okay, so let's come up with some definitions here. Let's say that, and always we're going to have this set B in the background if things we're avoiding, so I'm just not going to write that. So assuming that we got some set B, I'm going to write T pi to be the subtree rooted at pi. And what we notice with the complete binary tree is that all of these subtrees are also complete binary trees. They're all isomorphic. And so in this example, well, T12 is isomorphic to T1. And what we want is a formula for T1. Well, the idea with a generating tree approach is we want to find these places where we have isomorphic subtrees. If we only have finitely many isomorphism types of these trees, then it's fairly easy to count. Okay, because we'll come up with rules saying that, well, here we just come up with a rule that says that T of 1, 2 produces 2 things isomorphic to T of 1, 2. Okay, so we want to look for reducible elements. Here's the definition. I'm going to say the element pi of I is generating tree reducible if its tree, the tree of pi, is isomorphic to the tree of the permutation where I remove I and I relabel. Okay, so first of all, please stop me throughout the talk if you have any questions, but really I should be saying like standardize that or something because this isn't really a permutation. But that kind of thing is going to happen all over. So I'm just going to implicitly standardize whenever I remove something from a permutation. Okay, so in our example, well, they were all isomorphic. Right? Everything was isomorphic to everything else. So, for example, T12, and with that basis, with that capital B, is isomorphic to T1. So any element in 1, 2 is GT reducible. So I'll just take the 2. And like I said, if we can come up with if there's only finitely many isomorphism types, then we're going to be able to enumerate it pretty easily because we'll be able to say that, for this isomorphism type, its children are these isomorphism types, then we'll know their children and so on. And you can get it out of the transfer matrix method. So here's the theorem. And people were doing this by hand. And Theorem, back when I was a graduate student, encouraged me to look for automatic ways to do this. So this is the theorem. Following our equivalent. 1. There's a bound on the number of children in this tree. And again, there's some set B of permutations we're avoiding in the background. But we make the tree and we find that there's a bound on the children that's equivalent to step 2. Every sufficiently long permutation has a GT reducible element. And I guess really I should say every sufficiently long permutation that avoids this stuff. Okay, and this is the consequence I've been mentioning throughout. If everything that's long enough has a GT reducible element, we only have finitely many isomorphism types, so we can compute the rational generating function easily. And another way this is often said is that we can label the generating tree with only finitely many labels. There's a fourth condition that I'm not going to focus on. The fourth condition actually lets you stare at the set B and know immediately whether or not this applies. Okay, so that would be number 4. But you can tell before you start if it's going to work. And then the other thing, I mean, in order to actually implement this in the computer, you want to be able to test for these GT reducible elements. And so that's the other result. This can be automatically tested. Okay. So the Maple can just go through and, for each element, is it GT reducible? If it is, then that permutation reduces. Otherwise, we have to look at its children. We go through all their entries. And eventually, if we satisfy this unwritten condition 4, we're guaranteed that we have this generating function. Okay, so this went off in a couple different directions. So this was finitely labeled generating trees. And I wrote a Maple package called FinLabel. And then the next one I'm going to talk about is this thing called the insertion encoding. By Linton and Ruskuc. Despite the dates, it was inspired by the finitely labeled generating tree results. They just published it in the electronic journal, whereas I used an old-fashioned paper journal. So this actually did come afterwards, and that's what I want to talk about next. So these guys have a lot of expertise dealing with formal language theory. So when they saw this rational generating function conclusion, and they saw all this nice repetition, they thought there must be a regular language explanation for this behavior. And what they found actually is that if you use the regular language viewpoint, you can go quite a bit further. So this notion of a configuration which is a permutation with Okay, and the slots are going to be places where we will insert an entry. In fact, we have to insert an entry, but we haven't yet. So here, we must insert an entry. Okay, and then they had, well, insertions, which are where we insert a new greatest entry. And probably it's easiest if I give an example. So the slots are going to be diamonds. So we always start with a diamond. We're going to have some entry in this permutation. And let's say my next step, I say, okay, I want to put the 1 in the diamond, and I want elements on both sides. And then the next time I'm going to say, okay, the 2 is going to go before the 1. So I'm actually building some specific permutation. You just don't know what it is yet. And now let's say I put the 3 after the 1, but actually I'm going to put it right after the 1. And now, let's say I put the 4 in here. But actually, I've decided that the 4 is going to be the only thing in its slots. And now I'll put the 5, let's say, over here. I'll put the 6 over here. So this is a way to build this permutation 624135 by inserting only into the slots. And you see that when we insert into a slot, there's a few things we can do. This first one we can insert in the middle of the slot. I'll encode that with an M, and I'll subscript it with 1 because it's the first slot from left to right. Here, we took the first slot from left to right again, and we put a 2 in there, and we put it in the middle of the slot, splitting the slot into 2. So it's also an M1. Here, we put the 3 in the third slot, and we put it on the left. So we'll encode that with L3. The 4 went into the second slot, and it was the only thing there, so it filled it. So that'll be an F2. And then we filled the second slot again, and then we filled the first slot.
So it's again some moves, some bigger moves.
Yeah, you can think about it that way. And notice that this sequence is unique for this permutation 624135. So I can just encode this as its word. Its word was right up here. Its word was M1, M1, L3, F2, F2, F1. So we're clear on the construction here. So we've got this bijection between permutations and some words with letters M, L, there's also an R, of course, and F, subscripted by various slots. Now, of course, if I look at the set of all permutations, the number of slots I'm going to need is going to be infinite. Well, unbounded. Sorry for mentioning infinity. So I want to restrict the number of slots. And that's basically their theorem, is if we can restrict the number of slots, then now we've got a finite alphabet, because we only need middles up to so far and fills up to so far. So we get a finite alphabet, and actually whenever this happens, we have a regular language. So, yeah, notice that so far nothing depends on what we're avoiding. And also notice that the things we want to count are permutations. Now, permutation is also a configuration. It's just a configuration without any slots. So we want to count the slotless configurations, but we have to pay for this approach by having the slotted configurations around. We need a slight definition. Is this a B-avoiding configuration? That's, well, any configuration that can be extended to a B-avoiding permutation. obviously if I'm trying to count AVB, I can restrict myself to be avoiding configuration. Because once I know you're leaving the class, I don't care about it. Okay, so here was the theorem. Following our equivalent. One is that there's a bound on the number of slots. You're going to be avoiding configuration. And I'm going to skip 2 for now, and I'm coming down to 3. The insertion encoding. So, in other words, I mean the language of words. So like this M1, L3, F2, F2, F1, they correspond to permutations in AVB. So I'm going to call it the insertion encoding of AVB. Forms of regular language. Now, if you don't know anything about regular languages, that doesn't matter. This just means that there's a nice recurrence to compute these numbers. Okay, we'll get a more concrete version of this in a minute. Okay, so they proved this theorem, and that was enough to show that the insertion encoding is strictly more general than the finitely labeled generating traits. Now, about 2 years ago, I wanted to actually use this to do some computations for some other work that I had. And I found out that it was completely useless for what I wanted to do unless I wanted to work out these languages by hand, which I didn't want to. So I had to reverse engineer a way to do this with Maple. And I want to talk about that because that ties into the extension of enumeration schemes here in a minute. So I'm going to say that 2 configurations are indistinguishable. Well, here, some definitions I should give. I claim they're pretty intuitive. So if we look at like this configuration, slot 2, slot 1, 3 slot. That was built with the word M1, M1, L3. One possible way to finish it is F2, F2, F1, which we took here. Okay. So I'm going to talk about 2 different configurations. And they're indistinguishable if, well, if the ways to fill them are the same. If So eventually we want to fill these to get rid of all the slots. So I'm going to say that they're indistinguishable if it's exactly the same sequence of insertions fills them. Yeah?
Do you mean ways to fill them while still avoiding some set of permutations, or?
Yeah. So this is 4B. And then this is we're going to fill them 2 permutation. And actually, fill is a bad word, and this is a bad example. Instead, I want to let's look at this example. We're allowed to still create more slots, but at the end of the day, we have to get rid of all the slots. Okay, so they're indistinguishable if, basically they react exactly the same under these insertions. Anything that creates a pattern for one would create a pattern for the other. And then I want to talk about reducible entries here. So the entry C of I of the configuration I C, sorry, is IE reducible if C, and again, I should probably relabel this, but C and C minus I are indistinguishable. So what this says is that as far as the insertion encoding is concerned, that entry C of I doesn't play any part in whether or not we contain a pattern from B. So essentially, if that entry C of I doesn't play any part in whether or not we contain something from B, as soon as we produce this configuration C, we might as well regard it as identical to this configuration C minus C of I. So if every long configuration has an IE reducible element, then we can reduce it to finitely many configurations, and we can just run that in, walks in a directed graph or the transfer matrix method. Okay, and so that was theorem. This is part 2 that I added. Well, it was just published this year. Every sufficiently long B avoiding configuration has an IE reducible element. And another thing that's, well, so one thing that's nice about having this view is that Maple can just go through the configurations, and if it finds one of these, it just says, okay, well, I don't need any permutations around that have these reducible entries. And so it can pretty quickly build the insertion encoding. So now I have my Maple package that I wanted.
So in other words, you automated the ALR Maple?
Yeah, automated that. The other thing that you can see when you look at this definition of IE reducible is if you have a GT reducible element, that's actually IE reducible for any configuration whose underlying permutation is the one with that GT reducible element. So we get this inclusion right here immediately from the fact that a GT reducible is an IE reducible. And the other advantage is that the ALR proof with the regular languages was about 10 pages and had all these sort of exponential explosions when you determinize non-deterministic automata. And this way we just avoid that, and we get to a quick way to enumerate the class.
So you also simplify it.
Yeah. So the proof of that result that I've highlighted there too is like under a page. So it's an under a page proof of the theorem.
And can ALR do many more things than if enable?
You can. That's why I actually wanted to use it. But to use it, I had to do this first.
So how many more? What percentage? Yeah.
Well, the percentages here are always 0 in the long run. So back when I did this fin label, shortly after that, this was sort of annoying, but I realized that these were all special cases of things that could be done with enumeration schemes. And the package WILF of Zeilberger back in 1998. Now the advantage of fin label was it could get this rational generating function and it could redo exactly what people were doing, but anything that it could do, Zeilberger's algorithm could do. So basically for the rest of the talk, I want to briefly describe this and then talk about what we'd have to do to find some algorithm that can do